Another interesting example deals with wind acting on an object. In this example, we have a pilot flying a plane, flying at 168 miles per hour. Okay, that's the speed of the plane. She wants her flight path to be on a bearing of 57 degrees 40 minutes. Remember, when we use bearings like this, they come down from north. So north is considered 0, and you come down 57 degrees 40 minutes. There is a wind blowing out of the south, or from the south, at 27.1 miles per hour. So there's a wind pushing her up from where she actually needs to be going. Find the bearing she should fly and the plane's ground speed. Okay, so here's the thing is, she's going to have to compensate for that wind, which means she's going to have to veer a little bit further south in her direction and let the wind push her back up to the final bearing. And so the combination of the two, the bearing she should fly and the wind should give her this final bearing. Okay, so this is where she actually wants to go. So what we need to do is we need to add two vectors together to find this final vector. And so the vectors that we're going to add are the vector that, or the bearing that she needs to fly in, okay, in addition to the vector of the wind, which we know the wind is blowing from the south, so it's blowing sort of vertically here. Okay, if I can get that drawn nicer. That's not nicer. Okay, something like that. It's going to create a vertical force there on the plane. And so together, those two vectors added up should give us the third final vector of her final bearing. Okay, so we know that her actual speed that she's going to be traveling on is 168 miles per hour, right? 168. That is the magnitude of the first vector. The second vector is the wind speed, which is 27.1 miles per hour, okay? And so what we want to know is what this angle is coming down to the blue vector. That's her, that's the bearing she should fly. And then we also want to know the plane's ground speed, which is actually the speed along the final vector. Okay, that's the speed that takes into account her plane's speed and the wind together, okay? So we're going to need to find the magnitude of that red vector in the end. So two things we need: the angle for the blue vector and the magnitude of the red vector. Those together should give us our final answer. Okay, so how do we find all this stuff? Well, let's step back and look at it for a moment. We have some information for a triangle, right? What I don't know, well, if I look at just this triangle here with the blue and red vectors, I have two sides known. It doesn't appear that I have any angles known, but consider this. There's two parallel lines in here, right? My north-south line and the southerly wind direction, right? Blowing out of the south. And so these are parallel lines, and there's a transversal. The red line is or the red vector is a transversal. And so if I want opposite interior angles are going to be congruent. This 57 degree 40 minute angle is actually opposite interior to the upper right angle in the triangle. So I know that one, right? So that angle up there is also 50, maybe I should redraw this a little bit bigger. Okay, there we go. So this is a 57 degree 40 minute angle up there. A 27.1 side, a 168 side. Okay, and so now if I can find this other angle down here, then I'll be able to add that to the 5740 to get the final bearing. Okay. Let's see. So what I end up with is an side-side angle situation. Remember, these are the ambiguous cases. Side-side angles are ambiguous. And so it all really depends upon comparing the different sides of the triangle to figure out how many triangles we have. Well, I'm going to assume there's probably one here, rather than none. Remember, well, or two. But it could be any of these, so we've got to be careful. So, let's see. I do know that the 57 degree 40 minute is going to be an angle that's larger than this one. How do I know that? Well, the opposite side is larger than the other opposite side, okay? So my angle down here is definitely going to be an acute angle. So I don't have to worry about determining a first or second quadrant angle, okay? So law of sines is not going to be helpful here because I don't have opposite, or could I use law of sines? Yeah, I have law of sines. Never mind. I don't know what I'm thinking there. Law of sines is going to be useful. I have an angle and its opposite side, so I can fill in one of the ratios. So let's give this some labels. Let's call this A. No. Let's relabel. Let's call this A up here, B and C, and then this will be little c, little a, and this will be little b on the diagonal there, okay? Okay, so that gives me some labeling just so I can plug stuff in. All right, so just trying to think this through. I'm trying to reorient myself. Obviously, I'm tipping my head around. And the trick to this is the length of 168, because it is longer than the other side of 27.1, I know there's only going to be one possible triangle here, okay? Consider this. If I were to draw a perpendicular from B to the opposite side, if my side A was shorter than that perpendicular, I wouldn't be able to get a triangle out of this. Okay, there'd be 0 possible triangles. If side A was in between this height, I'll call it H, if it was between that height and C, there'd be 2 possible triangles, right? I could swing one here, I could swing one on the inside, and I'd have 2 possible triangles. But because 168 is longer than 27.1, there's only one possible triangle. I swing it out here. If I try to swing it the other way, I'm going to go outside of the triangle, okay? So I know there's only one possible triangle. Again, this is our ambiguous case, but I can determine there's only one triangle because only one triangle because A is greater than C, okay? So now I can use my law of sines and I don't have to worry about the ambiguity in that. I also know that when I solve the law of sines that this is going to be an acute angle, right? I don't have to worry about trying to go to the obtuse angle on the second quadrant. So I know that little a over the sine of A equals little b, little c, sorry, I have c given at me, over the sine of C, angle C. And so I plug in the 3 things I know, which are side A is 168. The sine of A is, let's see, sine of 57 degrees 40 minutes. Side C is 27.1. And angle C we don't know. So now I do my cross multiplying and try to solve for big C. So I get 168 times the sine of C equals 27.1 times the sine of 57 degrees 40 minutes. Okay. If I divide out the 168 and then apply the inverse sine, you guys have seen me do this a lot, so I'm going to run through that kind of quickly. I know angle C then is going to be the inverse sine of that fraction right there. 27.1 sine. Now when I do this sine, when I type it in my calculator, remember I'm going to do 57 plus 40 over 60. That gives me my minutes, right, as a fraction of degrees. So it'd be 57 plus 40 over 60. That's what's going in my calculator. All over the 168. Okay, so I'm going to type that in. I wrote it up here as though I was typing it in the calculator, kind of. It's structured a little differently. I'd have it all horizontal on the calculator. So, but at least you can kind of see what I would do. So I'm going to go inverse sine of 27.1 sine of 57 plus 40 over 60, close parenthesis, divide by 168, close another parenthesis. And that gives me 7.8 roughly. Now this is an angle. I should, in theory, try to put the angle in the same form as the original angle given. So I got 57 degrees 40 minutes given. I should put this in degree minutes. So, or maybe degree minutes seconds, depending. Do I want degree minutes? No, we'll just go degrees and minutes. So this comes out to be approximately 7.8337 and some other decimals in there. Okay, so that's a very narrow angle right there, right? Not a whole lot going on there. Small angle, but it's still significant enough. Like if you're flying a plane and you're off by 7 degrees or 8 degrees on an angle, you can miss your destination by hundreds of miles, right? You know, that small angle can result in a big difference in your destination. So you don't want to do that. Imagine if you were trying to fly a rocket to the moon, you could blow by the moon by thousands of miles and not even come close. So these little angles, what we think might be little, are fairly significant. Okay, so then I'm going to convert that into degrees and minutes. So I'm going to take my decimal, I'm going to subtract off 7, so I just have the decimal, and I'm going to multiply that by 60. And that's almost 50 exactly. I don't know if you can see that. So I took my angle that I found, subtracted 7 off to get the decimal portion, to multiply that by 60, and that gives me 50 minutes. So essentially we have C is approximately 7 degrees 50 minutes. Okay? So now if I were to add that to the original angle, because that's what we want for our bearing, we've got the original 5740 and then add this little bit in here, that would give me the final bearing. So 57 degrees 40 minutes plus 7 degrees 50 minutes. Well, the 40 and the 50 make 90 minutes, right? Well, 90 minutes is the same as 1 degree 30 minutes if you take 60 off of that. So that's 1 degree 30 minutes. 57 and 7 make 64. And if I add a 1 degree 30 minutes, that's really 65 degrees 30 minutes. That is the final bearing that she needs to be on in order to get to her destination. Yep, okay. Just checking that in the book, make sure that's right. It is. It's good. Okay, so now we found that, but we haven't found her ground speed yet. Her ground speed, remember, is the magnitude of our red vector. And so I would need, let's see, well, I need to finish solving my triangle, really. I can't get B, the ground speed is essentially B. And I can't get that without knowing angle B, which I can find now because I have the other 2 angles. Yeah, these 2 angles. No, which 2 angles do I have? Yeah, I have the 5740 and I have this 7 degree 50 minutes. So if I take those 2, add them up, which I've already done, and subtract that from 180, I'll get angle B. So angle B is 180 degrees, 0 minutes, minus 65 degrees, 30 minutes, okay? Now, I want to do a little borrowing. Remember, 180 degrees is the same as 179 degrees, 60 minutes. If I pull 1 degree and split it into minutes, that's how I would borrow on that one. And then do the subtraction. 60 minus 30 is 30 minutes. 179 minus 65 is 114, right? If I'm doing my subtraction right. Subtract 4, yeah. That looks good. Okay, so 114:30. And so now I can use the law of sines again to find this side B. So let me erase a little bit of this work from the previous angle, and we'll substitute everything in that I need. So now I'm going to go with, let's see, side A over the sine of angle A equals side B over the sine of angle B. Now I'm going to have to just accept the fact that there's a little rounding error in here because I'm not going to go back and try to use all the decimals. Okay, so side A is 168. Angle A is, so this is sine of 57 degrees 40 minutes equals B, which I don't know, over the sine of angle B, which I do now know, is 114 30 minutes. Okay, well, I know 30 minutes is half a degree, right? So that I could just round that. I could just call that, not rounding, I could call that 114.5. It'd be a little bit easier on the calculator. Okay, so now I'm gonna just, if I just multiply by the sine, 114 degrees 30 minutes, do that on both sides, and I'm not gonna write it all in, but you know what I'm doing. I'm multiplying both sides by that sine, so that B, little b, is equal to 168 times the sine of 114 degrees 30 minutes all over the sine of 57 degrees 40 minutes. Okay, and so I just type that in, 168 sine 114.5, that's a 0.5 angle, divided by the sine of 57. Now here I'll do plus 40 over 60 to get my minutes, and there we go. It is approximately 180.9259 ... So because my original speeds were rounded, I guess I had 3 significant figures here, right? I've got 3 non-zero digits in each of those speeds. I could just go to 3 non-zero digits. We'll call that 181. Double check that. Yep. So we're going to round that off. We'll call that 181 miles per hour as the ground speed. Okay? And so that gives you all the information that we're looking for. That completely solved the triangle, by the way, in doing so. But it gives us both her bearing and her ground speed. So if she wanted to know then how, what angle she actually needs to point the plane at to get to her desired angle, it's going to be different than where the desired angle is, right? Because the wind is pushing her as well. So she points the plane at a bearing of 65 degrees 30 minutes, and she's going to actually travel at a bearing of 57 degrees 40 minutes. She's also going to be traveling with a ground speed of 181 miles per hour, even though her plane is traveling, she's flying at 168 miles per hour because the wind is giving her an extra boost. Okay, so if she wanted to figure out, for instance, how long it's going to take to get to her destination, she would use the distance, the actual distance between her location and her destination, and multiply by 181. I meant divide, sorry. Distance equals rate times time. To find the time, you would divide distance by rate. So you would divide the distance by the 181 rather than by the 168. That's a fairly significant difference if you're trying to be fairly accurate in your arrival time, okay? So all these things go into figuring out flight plans, bearing angles, your arrival times, your departure times, all those things are kind of factored in, and things adjust based upon the wind, based upon the weather, and so there's a lot of uncertainty when you go to fly a plane as to some of these details until you know some of the information about the weather, the wind, and so forth. Okay, but it can be calculated. We have computers that can do a lot of this for us now, but some of this still needs to be done by hand or on a calculator last second. So kind of interesting stuff, and it can all be done using trig, law of sines, law of cosines.